or chemical principles topic. So understanding a little bit more about where a reaction lies, whether it's towards the reactants or towards the products. So we have a lot of learning objectives to get through. So unlike class on Monday, which was a lot of easing us into review and things like that we've already seen and introducing a few topics, we're kind of getting into this chapter really fast. So lots of arrow pushing today, lots of mechanisms. All right, let's go ahead and get started. So again, this chapter is about aldehydes and ketones, chapter 18. So we're going to learn about the 4 P's. So this is learning objective 18E. And this is the 4 P's of nucleophilic addition of watered aldehydes and ketones. So in this learning objective, we see that water is going to act as our nucleophile. And aldehydes as ketones, as we discussed, are pretty good electrophiles. So that's going to be our electrophile. And the functional group that we're going to form here is going to be called a hydrate. So that was one of the functional groups that I asked you all to kind of think about at the end of last class. So if you're following along, this is chapter 18.6. All right. So let's go ahead and take a look at what this looks like. So we have our aldehyde or ketone. It depends on if one of these R's is a hydrogen, if it's an aldehyde, versus if they're both, R's are both carbon-based groups, then they're ketones. And we said this is going to be our electrophile in the reaction. And then we're going to have a nucleophile. So this is going to be water, which is our nucleophile. Or I will tell you, we're going to talk about this under acidic and basic conditions. So I'm going to say, or it's used to generate nucleophile, because sometimes our nucleophile, depending on our conditions that we run it under, are going to be hydroxide. So it comes from the water ultimately. Then this is where our equilibrium comes in, and we'll talk about how to figure out where the equilibrium lies. So we have equilibrium arrows and a catalyst. All right, an acid or a base catalyst. And then the product that we're going to get is one of those new functional groups that we learned about, which is our hydrate. All right. So when we're thinking about our catalyst, we can do this under multiple types of conditions. We can do this under basic conditions or acidic conditions. So if we use an acid, we can use something like H2SO4 as an example. And this acid is going to increase the electrophilicity of the electrophile. Right, we saw this, on Monday, where we were protonating a lone pair on that oxygen, making it more electrophilic. So we can either increase the electrophilicity of one of our starting materials, or we can run this under basic conditions. Our base catalyst, for example, could be sodium hydroxide. And what the base does, it increases nucleophilicity of our nucleophile. All right, and this is because aldehydes and ketones are not the most reactive functional groups that we've learned about, right? So just like an electrophilic aromatic substitution, sometimes we have to increase the reactivity of our coupling partner for it to be able to react. All right, so we'll talk about the mechanism for both of these. So this is the first time we're going to go through a mechanism that is going to look like this. So we'll talk about actually the base catalyst first. All right, so this is where we're making our stronger nucleophile. We should know intuitively that water is not a super strong nucleophile, right? I mean, we're like drinking it all the time. If it was a really strong nucleophile, it would be very reactive in our bodies and we'd have a lot of problems. All right, so let's see what we have here. So we can take an aldehyde or a ketone. I'm not going to worry about which of these species that is. And when we're going to increase the nucleophilicity of something, I'm going to draw these equilibrium arrows here. And we're going to say that our nucleophile is going to be catalyzed by sodium hydroxide. It's going to end up being a catalytic amount of sodium hydroxide, and we have water in this reaction as well. All right. So throughout this process, we're going to regenerate sodium hydroxide from water. All right. That'll be part of our mechanism. Okay, so our first arrow needs to start from lone pairs. We see that hydroxide is the most nucleophilic thing here, so we can take the lone pair on hydroxide and we can go ahead and have that attack our electrophilic carbonyl carbon at the 2 position. That breaks this double bond between the 1-2 positions and returns those electrons to our oxygen. All right, so that gives a negatively charged oxygen. We can use sodium as our counterion here. And then we have our hydroxide that has added in and made a carbon-oxygen bond. All right. So we know it's okay to have a negatively charged species here because we're under basic conditions. If we're under acidic conditions, we're not going to want to see too many of those negatively charged species. And here's the part where water ends up being turned into our catalytic amount of hydroxide again. So we can take this alkoxide oxygen lone pair with a negative charge. We can deprotonate water, and that's going to return our sodium hydroxide catalyst, and that's going to end up as our product. All right, so we can draw it like this, which is the exact same thing as if the oxygens were up. It doesn't really matter. We're not indicating any sort of stereochemistry here. And then, of course, we've regenerated our sodium hydroxide. So at the end of our mechanism, we know it's likely right because we regenerated our catalyst. All right, so we just need a tiny amount of sodium hydroxide to kind of kick things off, and then we can run this reaction in the water. All right, so when we're thinking about this nucleophilic addition, this is something we've seen before. We've seen a lot of things add to electrophiles that are aldehydes and ketones. So this shouldn't be too new for us. Let's take a look at the acid catalyzed mechanism as well. So in this case, we're making our electrophile more electrophilic. So we're making a stronger electrophile. In this case, we're not going to want to see a lot of negative charges like we did in our base-catalyzed reaction. So we can have our aldehyde and ketone to start out with. And then we can have in our reaction, we have our H2SO4 as our catalyst. So I'll draw this H kind of separated from everything else. Run this reaction of water. We know that H2SO4 is a really strong acid. Great, we can go ahead and take that lone pair of electrons and protonate our oxygen. Right, and that leaves us a positive charge on our oxygen. Right, because we've just protonated it. And then the counterion is, of course, SO3H minus. And we know that here we have our water, right? We didn't use it previously, so let's draw in our water here. Water, of course, has 2 lone pairs of electrons. It's not a great nucleophile, but we've made a great electrophile because we've protonated this ketone or aldehyde. So we're going to take the lone pair of electrons from water, and we're going to go ahead and have it attack that electrophilic CO double bond, which is going to break that CO double bond to form a single bond and then return our electrons to our oxygen. Right, so up top, we now have a neutral species, right? Unlike in our base-catalyzed mechanism where we had OH, O minus, and then we had to protonate it to form OH. We already have OH here, but we have our H2O here, and the oxygen is positively charged because we have not lost one of those protons yet. We can have our SO3H minus here. We have lone pairs on some of these well, actually we have lone pairs on all of these oxygens. If you wanted to use water to deprotonate this instead, I don't care. We can regenerate H2SO4 as well. We just need something that's a pretty acidic proton. We just need something to regenerate our catalyst. And then, of course, we've returned H2SO4 to its catalytic form. So we've again regenerated our catalyst in both of these cases. And this is why we just need a stoichiometric or more amount of water so we can regenerate this catalyst. I'll let you catch up drawing for a moment. Oh, question. Oh, yes, we can break that OH bond. Yes, thank you. So we've got to return that those lone pairs onto oxygen. All right, so this is how we're going to think about our acid and base catalyzed formation of these hydrates. All right, we're going to see this type of mechanism over and over again. Instead of water, we're going to add alcohols to form esters, hemiacetals and ketals, and acetals and ketals. We're going to see this kind of over and over and over again. So this is a pattern I would start to think about now and kind of get down. All right, so our next learning objective is, what do we do about these equilibrium arrows? Everyone's kind of uncomfortable about equilibrium arrows. So learning objective 18F is we're going to predict the relative equilibrium, or KEQ. So this is equilibrium for product formation. When we say relative, I'm not asking you for a value. I'm not saying like, 10 times, 5.02 times 10 to the minus 3 is the rate constant for this or something like that. I'm just saying when we compare across a series, how are we going to think about doing this? Right, so our reaction that we have is our aldehyde or our ketone. The relative KEQ we can think about under acid or base catalyzed conditions to form our product. When we're thinking about KEQ, that is equal to the concentration of your hydrate or your product divided by the concentration of your starting materials. I'll just say starting materials. All right, so we've already learned about some KEQs when we learned about esterification reactions, and we learned about our Dean-Stark trap when we were trying to pull water away from our reaction. Here, we're going to think about KEQ in terms of this aldehyde or ketone. So there's two factors we're going to consider. We're going to consider sterics, which is the size of the substituents that are around our reactive site. All right, so that's the size. And we're going to consider electronics. Right, both of these impact KEQ. Right, so when we're thinking about electronics, we're thinking about electron donating groups or electron withdrawing groups. All right, so we can sort of think through this exercise and then we'll do a couple of practice problems. So something is very, very large. It's going to be pretty difficult for our nucleophile to access this carbonyl carbon, all right? If these groups are really, really big, it's going to be quite difficult, all right? If these groups are really tiny, then it's going to be very easy for a nucleophile to come in and attack that carbonyl carbon, all right? So I think that's an important consideration. The other thing we need to think about is electronics. So if you have an electron withdrawing group here, this is withdrawing electron density away from our carbonyl carbon. All of a sudden, we have all of these things withdrawing electron density away, making that more electrophilic. If something's more electrophilic, it's more reactive, it's going to go towards product, right? So these are the kind of things that we need to start thinking about, and I'd like to think about them through a couple of examples. So we're going to do 2 chime-in questions in a row, all right? One that deals with sterics and one that deals with electronics. So we're on lecture 18 today. Let's see if it will load. Okay. So we're going to think about which of these favors hydrate formation the most. So if A is our electrophile, B or C is our electrophile. We're going to go ahead and see if we can figure out which of these compounds is going to favor the product. All right. So we are comparing across 2 different functional groups. We're comparing aldehydes and ketones. So we need to think about a couple of different factors there. We also need to think about the relative size versus hydrogen versus a methyl group. All right, so we have some people that have responded. So we'll go ahead and take a look at this real quick and see what people are thinking. All right, so we're thinking about, we have a little bit of a mixed score today, but we're thinking along the lines with A is that hydrogen is pretty tiny. So it's not going to be very sterically hindered. All right. And so hydrogen is going to favor the product formation the most. I like that people saw that tert-butyl group and said, no way, that's really sterically hindered. It's not going to favor product formation because the nucleophile will have a lot of trouble attacking it. And these methyl groups, we're thinking about methyl groups versus hydrogen, and methyl is CH3 versus just hydrogen. All right, so I think that's great. I'll leave this open for a little bit longer, and let's go on to our next question. All right, so let's see which favors the hydrate formation the most. So we have a CF3 group versus a CH3 group. So we can sort of think about where we think this equilibrium is going to lie. Which of these is going to react the most to form product? All right, so sterics is often a little bit easier, I think, for us to think about, where like something's really large, but sometimes electronics are a little bit more confusing. All right, so ultimately we're reasoning through the fact that this is an electrophile, so it wants to be more electrophilic. So let's see what people are thinking. Right, again, we kind of have some mixed answers here, and I understand why electronics is a little bit more challenging to think about. So I will go ahead and leave this open for a bit longer, and then we can go ahead and go through these chime-in questions. Okay, so we're thinking about sterics and electronics. So let's go through the answers here. All right, so we had the idea of our electrophiles. And it's always okay to draw things out. All right, so we have this electrophile versus a tert-butyl group, which was the least popular. So a tert-butyl group is a CH3, CH3, CH3. Sometimes it's easier to see things when we draw them out. Now I'm even going to draw out our methyl group, not just as a CH3, but as a CH3 with all of its bonds in. So if you're having trouble evaluating the steric profile of all these different things versus each other, I encourage you to draw out the group. So a methyl group is a CH3 group. So now it's a little bit easier for us to see, I think, that the size of this is very small. So this is the least sterically hindered. All right, so the most favorable product formation. right? And this is based on steric arguments, so the size of things. All right, so that was a little bit maybe more simple. So now let's take a look at when we have our methyl group versus our CF3 groups. Or sorry, yeah, our CF3 groups. So this is not going to be as much of a steric argument. Carbon and fluorine is very electronegative. It's actually very small. So comparatively, fluorine compared to hydrogen, let me draw this CH3 out. These actually are not going to have very different steric profiles, all right? So now we're looking at electronics, okay? So when we're looking at electronics, right, we want this to be a good electrophile, right? So if we want a good electrophile, we're going to think about the fact that our electrophilic carbonyl carbon, that oxygen's pulling electron density away from both of those options. Okay, great. So now let's take a look about these CF3 groups. Our methyl groups are mildly donating, so we don't have any electron density pulling that away, but we do in fact have a lot of electron density being pulled away from this CF3 group, which is very electronegative. All right, so CF3 groups are electron withdrawing groups. So ketone is more electrophilic, which equals more reactive, so favors the product. All right, so based on these examples that we learned, let me just circle this one here. Let's go back up here and say sterics, the size, the smaller steric profile is going to favor product, right? And we can say of electron withdrawing groups, the more electron withdrawing groups, the more electrophilic, and that favors product. Right, so this is often how we're thinking about electronics and sterics with every single reaction, right? So if we wanted something to be more nucleophilic, instead of on our electrophile or more nucleophile, we would say to ourselves, well, we want more electron donating groups because that increases nucleophilicity, right? So we're always considering what we're looking at, the electrophile or the nucleophiles. We start to understand these types of parameters, all right? So sterics and electronics are always impacting the chemistry. It's always the answer, sterics and electronics. All right. So we're going to throw back to another reaction that we actually already learned. We only learned the 2 P's of it, but we're going to recognize a lot of people missed this on the exam, I think, because you weren't understanding the mechanism of this reaction. It was part of our final product multi-step synthesis. So our learning objective 18G is to recall the 2 P's of aldehyde and ketone oxidation, right, to form carboxylic acids. You'll recall these are chromium reagents. And now we want to recognize a hydrate intermediate. Right? This is why our chromium reagents, we needed to have some water in our reaction. Okay, so what we learned was that if you have an alcohol, a primary alcohol, all right, we learned that when you add this potassium chromate, these chromium 6 reagents, and H2SO4 and water. When we didn't add water for example, our PCC oxidation, it stopped at the aldehyde. But when we added water, what we recognize is this goes all the way to the oxidation to the carboxylic acid. And that water is forming a hydrate intermediate, and that's why we can get to this final product, all right? We don't need to know all the entirety of these 4 P's, but what I want you to recognize is that we went through this aldehyde intermediate, right? We have acid in there, so we're gonna protonate it. This looks a lot like our acetal formation intermediate. Then we have water come in as our nucleophile and attack that carbon, break that CO double bond, and this gets us to a hydrate intermediate, which now we can understand sometimes for some people, it's really helpful for mechanisms and products to be aligned. So a lot of people miss the fact that with the chromium-6 reagents and acid and water, we went all the way to the carboxylic acid. And this is because we went through our hydrate intermediate. So for some of you, by understanding a little bit more about the mechanisms and intermediates, I think you'll have more success on this type of problem. So a lot of people got tripped up and said, PCC can do this, but we don't have any water, PCC or PDC, even though those are chromium-6 reagents. And so hopefully this will help people. All right, so we've looked at hydrates. So that's an oxygen-based nucleophile. Now let's take a look at what happens with a carbon-based nucleophile. All right, this is learning objective 18H. This is the 4 P's for cyanohydrin formation. Remember, we talked about cyanohydrins as one of the functional groups we needed to know. This is going to be from aldehydes and ketones. And a cyanide source. You can find this in chapter 18.7. All right, so what we need at the end of the day, we'll see how this mechanism works. But what we need at the end of the day is some form of cyanide. And we can have actually 3 sets of conditions that will work for this. All right, so we said we start from an aldehyde or a ketone. Right, this is part of our starting material here. And at the end of the day, we're going to have some form of acid and some form of cyanide. Right, this is also equilibrium situation. Hydrogen cyanide is not super acidic, so we can have the cyanide exist in the reaction. And let's go ahead and have the lone pair of electrons on our carbon go ahead and attack our carbonyl carbon. It's going to break our CO double bond and place those electrons back on the oxygen. This is exactly the intermediate that we saw under basic conditions with our hydrate formation. So now we have a new carbon-carbon bond with our cyanide group. We have our sodium counterion. We still have our HCN in the reaction. Right? So basically we just need a catalytic amount of our cyanide minus because our oxygen is going to deprotonate that HCN and regenerate our sodium cyanide. All right. So that gets to our cyanohydrin product. And you'll notice that we regenerated our sodium cyanide. It's ready to go for this next equivalent. All right, so this is very, very, very similar, you'll notice, to the acetal formation under basic conditions. But instead of a carbon-oxygen bond, we've just made a carbon-carbon bond. All right? So as far as our 2Ps go, for our starting materials and products, I have here for you that we need a CN minus source. I drew the incorrect number of lone pairs on this cyanide here. It should just have one. Sorry about that. So we need a cyanide source and a proton source. So we can have a number of different conditions in which we can get to the final product. So the one I just showed you was sodium cyanide plus HCN. Another set of conditions that we can use is in step 1, we can use sodium cyanide, or we could use potassium cyanide, doesn't matter, the counter ion. And then in step 2, we would add H3O plus, some sort of acid source. So we could do this stepwise, in which case we would have a stoichiometric amount of sodium cyanide, and then we would add in H3O plus after. Alternatively, we can actually just generate cyanide in our reaction by adding HCN and sodium hydroxide. So sodium hydroxide is going to deprotonate that HCN to form the cyanide minus. So any of these combinations are going to work. On a practical scale, HCN is like incredibly, incredibly, incredibly toxic, and it's a gas. So I would never let anyone in my research group use HCN. So that's why people have come up with alternative ways like option B. I mean, not to say that sodium cyanide or potassium cyanide is particularly good for you. It's also bad, but HCN is even worse. So this is often why we have multiple sets of conditions. All right, let's go ahead. And so we've added thus far, we've added oxygen as our nucleophile in terms of adding water. We've now added cyanide to form a carbon-carbon bond. At the end of the day, we end up with one alcohol in the product and one other thing. In the first example, we have 2 alcohols total, so 1 plus 1. Here we have another cyanide. Well, when we use alcohols themselves as our nucleophile, we're actually going to go twice, all right? So our mechanism is not going to stop here. It's going to just keep going. So that's our next learning objective. Learning objective 18I. This is the 4 Ps of formation of acetals and ketals. So acetals and ketals are some of the functional groups that you were studying from last time. This is from aldehydes and ketones. So, right, we learn the names. If you make a ketal from a ketone, you make a acetal from an aldehyde. And if you wanted to follow along in the book, this is chapter 18.8. All right, so we're only going to learn the acid catalyzed version of this, but it is a base catalyzed reaction as well. But the mechanism goes on for, well, we'll see, about 8 steps. So we're just going to learn one of them for now. Okay, so we start out with our electrophile, aldehyde or our ketone. Right, we're running this under acidic conditions first. So we need an acid catalyzed, meaning our electrophile is going to be more, a stronger electrophile. We're going to use 2 equivalents of an alcohol as our nucleophile. Right? So now we can start thinking about KEQ. If we have a very small R group, like a methyl, we can start to think about the KEQ favoring our products. If we had a tert-butyl alcohol, that would be pretty large. It might favor our starting materials. So we need to start to think about KEQ because this is at equilibrium. We'll use an acid catalyst today. What we form at the end of the day is we entirely get rid of our oxygen from our aldehyde or our ketone. And we end up with an acetal or a ketal. So this is why we needed two equivalents. So if it was from the aldehyde, we would get an acetal. If this was from the ketone, you would get a ketal. And so something as I always like to do is track what else happened in the reaction. So you'll notice here that we have two equivalents of our nucleophile that are missing H's, and we've lost that oxygen from our electrophile over here. So at the end of the day, we have our oxygen that came from our ketone, our aldehyde, and two hydrogens from our alcohol. So our byproduct here is water. Right, and indicate that the oxygen came from aldehyde and ketone. Right, so the reason I'm telling you that is this will help you understand the mechanism more. You need to figure out in this mechanism, are you making an OR1 bond or are you making an O carbon bond, right? And if we understand the oxygen goes away entirely, it's not part of our reaction. We know we're not having it react with our OR for some reason, okay? So we can think about this equilibrium, right? We can think about this. So we can drive the equilibrium forward by removing water. Right, we learned this in Fischer esterification. Right, we said that you could use, for example, a Dean-Stark trap. And that removes water from your reaction. Okay, you can remove other water in other ways as well. So we can, it's sort of, I'll just say from Dean, for example, Dean-Stark trap or other Fischer esterification conditions. So you can look back, we could add more of our starting material. We could, either of our starting materials. Right, anything that goes with equilibrium is gonna work for us here. So this brings us to an interesting question about our acid catalyst. What is the best acid catalyst to use? Well, we often use sulfuric acid as an acid catalyst. It doesn't have a great nucleophile with it, but sulfuric acid is oftentimes made in water. So if we want to focus on our equilibrium, we need to think about the fact that we've made this in water. So our acid catalyst can be H2SO4, but this is not going to help with our equilibrium very much. It can be HCl, which can be in aqueous solutions or not, but we also use something very commonly called tosic acid. We abbreviate this TSOH. Tosic acid is even a abbreviation for toluenyl sulfonic acid. So this is what tosic acid looks like. It's a very strong acid. It looks a lot like sulfuric acid. Let me draw it a little up a little bit more so you can see it better. So the toluenyl sulfonic acid part of tosic acid comes from, it has a toluene group in it or a methyl group. Then we have our sulfur groups and our OH. This looks a lot like a sulfuric acid derivative, right, has very, very similar pKa. So we often use tosic acid as our choice in this, but we can use the other ones. But tosic acid doesn't come with water, so it's a lot easier to drive our equilibrium forward. All right, let's get into this mechanism. Okay. So it's going to start out just like we've seen before, all right? So we're going to start out, we know when we have, for example, tosic acid in our reaction or HCl in our reaction. I'm going to do this on benzaldehyde. We have some sort of H plus in our reaction. We can go ahead and let's just use HCl. We could go ahead and we can protonate our oxygen. Right, so we've seen this step before, just like when we had our acetals and our ketals. We now have protonated this oxygen plus Cl minus. We just made this into a better electrophile. Could have been tosic acid, doesn't matter. Now we need our nucleophile to come in, and our nucleophile that's going to come in, let's use ethanol as our alcohol. Right, just like we saw in acetal formation, our nucleophile comes in and attacks this more electrophilic carbon of this CO bond. We break that CO bond and we return our electrons to our oxygen. All right, so now we have an oxygen that is now neutral, it's protonated. And now we have our ethanol that was added in that is positively charged. We have our Cl minus as our counterion. All right, so now we can get to an intermediate that looks a lot like our acetal that first time, all right? We can do a proton transfer here. You could do this from another equivalent of ethanol. I'll use our Cl minus. We can deprotonate that OH bond, return those electrons to our oxygen. All right, so now we get to this intermediate. I'm going to draw, just so it's out of the way, our ethanol on the top instead, but I've just done a bond rotation. And now we've returned HCl as our catalyst. We still have this H plus and this Cl minus. So this looks very similar to our acetal intermediate, but let's take a look at our product. Our product has two equivalents of the alcohol that is now added. Okay, that means we have some lone pairs of electrons on this alcohol that needs to leave to form water. So let's go ahead and turn it into a good leaving group by deprotonating it. And our equilibrium continues. So we haven't done anything with our alcohol on one side, but we have protonated our alcohol on the other, I guess our ether on the other side. All right, so now we get to this product. We'll carry through our Cl minus. Now, this is something that we have not really seen before. A lot of people really want to do an SN2 reaction. They say, I really want to take another nucleophile. I want it to attack here and have water leave. But we don't want to do an SN2 reaction, especially if this is a ketone. So we actually are going to have our lone pair, and the reason is steric hindrance. So what we're going to do is we're going to have our lone pair of electrons on our oxygen of our ether, our ethyl ether that's already formed, come down and form a CO double bond, and that causes our water to leave. It's not a very good looking equilibrium arrow. Okay, so our water has now left. So we have H2O that is now left. Now our intermediate looks like this. We now have a carbon-oxygen double bond, but instead of it being protonated like we would have had before, we have this ethyl group bound to it, right? But this looks exactly the same, this protonated oxygen of this aldehyde. The only difference is we have our ethyl group, which I'm sorry, should be in blue. That's the only difference. So this is going to react the exact same as our sequence above, right? We're going to have another equivalent of our ethanol come in. Now we see that's a very electrophilic carbon because that is a positively charged oxygen. We're going to take a lone pair of electrons of our ethanol. It's going to go ahead and attack, break our CO double bond to make that a neutral species. And now this looks again just like an intermediate that we have seen before. We still have our proton bound to our ethanol. We're carrying through our Cl minus as well. And now we see this intermediate here looks pretty identical to this intermediate here in the mechanism, all right? So we can say that our chloride is going to come in and, or another equivalent of ethanol is just going to go ahead and deprotonate, all right? And that gets us to our final product. That also regenerates, our HCl is now regenerated. And we get our product, which is the two equivalents of ethanol to form our acetal. All right, so this looks like a really complicated mechanism. The thing I want you all to focus in on is a lot of people struggle with this intermediate. They really want an SN2 reaction to happen here to cause our leaving group. The reason why we're not doing that is an intramolecular reaction within a molecule to have this lone pair come down and cause the water to leave to generate this intermediate. Intramolecular reactions are always faster than intermolecular reactions, all right? So that is why we have this reaction proceed as it does. Now, once we get to this intermediate, it looks quite familiar to what we've seen before, as does this, and we get to our final product. All right. So while this is many steps, we basically see it repeated twice to generate our product. All right, that is it. Thanks everyone for braving the snow to come in today.